to the central limit theorem here. Okay, all right. Central limit theorem, right? So we're going to be learning everything about central limit theorem. Okay, central limit theorem for population proportion, and population mean. Okay, why is central limit theorem so important, right? Okay, the fact that we cannot, okay, so we're using a sample, what we call the sample proportion and sample mean, and before we didn't have to actually deal with what we call the central limit theorem. Why? Because since we knew about a population standard deviation and population mean, we did not needed what we call the central limit theorem. Okay, central limit theorem. If you kind of has all of you guys read this through? Okay, it says if we were to go through and calculate many different sampling distribution over a long period of time, we will start to see that many of them share a similar format. Individual distribution will, of course, have variation between them, but will have enough in common that they are able to group and analyze together. Okay. Fortunately, a bunch of statisticians that came before us did all that already, and now we don't have to do it. Okay, we will trust in the work of previous, right, scientists or mathematician, and we'll rely on their prior knowledge, right? We can't just coast on their accomplishment, right? All right, so we'll probably work really hard on what they found and where it can take us in more accurately, right? So, all right, enough preamble. Let's go through the good stuff here. Central limit theorem is the result that lets us jump straight to what sampling distribution, right, will look like. Okay, sampling distribution will look like, basic idea is that it's going to be looking very similar to that, what we call the normal distribution. Okay, it's going to be normal distribution. Okay, they're saying that if you take a sample and then if you actually do a sample distribution of the sample, right, then what they're saying that is always going to be represented as a normal distribution if it meets the condition of what we call the central limit theorem. If it meets this condition of the central limit theorem. Okay, basic idea. If it meets this condition of central limit theorem. So first we'll get, okay, what do I mean? Let me give you a layman's term. Okay, so suppose that I own a fishing shop. Okay, and I do not want to pay for my inventory. I have a huge backyard that has a lot of worms. Okay, so for bait, I sell worms, right? Okay, I have a huge backyard, right? Okay, there's a bunch of worms in here. We have worms crawling everywhere. Okay, worms. Okay, and all I need to do is go back and then dig them. Okay, so first we get, any question? Okay, now what I do is I go out and then dig, right? And then I find 10 worms and then box them up. Okay, so when I box them up, so I go out and dig, right, with the shovel. With the shovel, right? I go out and dig with the shovel, right? And then, right, and I box those up, right? So when I get my first box right here, suppose that this box weighs 1 ounce. Okay, a worm, those 10 worms. Okay, I have 10 worms here. Okay, this box weighs 1.5 2 ounce. Okay, this box weighs, okay, because they're not all equal, right? When I actually box them up. So what do I do? Okay, when I actually gather all this, right, and then I box, and then normally, right, we'll gravitate the middle, right, what we call a mean value. And suppose that the mean is actually 1.5 ounce. As we pick up these and then make up boxes, usually then we could actually stack them up. Oh, there's 1.5, right? And we have 1.5. We had a little 1.2 we had over here, 1 point. So 1 here, maybe we have 1.8 here, right? 1.6 here, and so forth. And then if we actually stack up the boxes, it will come out to be, stack up the boxes of worms, it will come out to be very similar to that of what we call the what? Normal distribution. Get the idea? Okay. And that's what is going to come out. Okay. Rather than having 10 worms, okay, what if I use 100 worms? Would that be a better representation? Would they get closer to the mean value? Yes or no? Destiny?
No.
Yes or no? 100? Wouldn't you think about this? So if I put 100 worms here, and if I figure out the average weight of the 100 worm, would that be average weight of each worm? Would that be closer to 1.5 ounces there?
Oh, then yeah.
Yeah, right. It'd be closer and closer, just like you did with the what was it? What was that problem? Gettysburg Address, right? Okay. So if you, or what was the other problem that you guys did? Oh, home run distance, right? You figure out, oh, let's use 100, right? Let's use 500, let's use 1,000, right? Get the idea. As we take more samples, it gets become bigger and bigger, right? But in central limit theorem, they tell us, oh, what is enough sample? What is that sample that we actually need in order for us to actually meet the criteria or conditions? Okay, in order for us to actually use a central limit theorem, it has to meet this certain condition. Okay, so first we'll get, okay, so central limit theorem is a result that lets us jump straight to what the sampling distribution will look like. The nice thing that for our course, everything we look at with central limiting is going to be a normal bell-shaped distribution. Okay, our job is going to be making sure that the CLT, central limit theorem, applies to a given situation. If it does, figure out exactly what the sampling distribution will be, and it's going to be a bell-shaped curve. Okay, they're saying that it doesn't matter if, so what central limit theorem, just excuse me for a second. What central limit theorem is telling us is that it doesn't matter your population distribution, okay? Doesn't matter if it's skewed to the left, if it's skewed to the right, if it's a uniform distribution, right? It does not matter, right? Long as if you take and if you meet the condition of the theorem of the central limit theorem right here, okay? Then we know that your sampling distribution will always be a normal distribution, okay? And what is the central limit theorem tell us for a sample proportion? It's saying that it's gotta be a simple random sample and it's gotta be independent, okay? And we talked about simple random sample, right? Why is it so important that it's a simple random sample? Okay, Alexandria, why is it so important that it is your sample is a simple random sample?
Because the data would be random, it's not like it's chosen or like.
Right. So better word, the word bias, it leaves out the bias, right? Okay. So you're not saying, oh, I want to measure the average height of Cerritos College students. So I'm going to go measure, basketball players, right? Or basketball team, the whole basketball team. That's being biased, right? Okay. Get the idea. So therefore, if it's a simple random sample, you're taking out the bias. So you're trying to figure out the true mean or true proportion. Okay, get the idea? So the first condition of your central limit theorem tells us that it's got to be a simple random sample. Okay, number two, your sample size has to be large enough. What do you mean by large enough? How do you actually know if we've taken a large sample, right? So like I said, if I want to measure the average height of Cerritos College student, is measuring a simple random 10 college student enough to represent the population? Yes or no? Atir? Is 10 people enough to measure or figure out finding the average height of 10 students? Is that going to represent the population? Yes or no? Is that enough? Atir?
No.
No, not enough, right? How about 100?
Yes.
Oh, how do you know? Is 100 enough, right? How do you know 1,000 enough? They're saying that the central limit theorem tells us, this is kind of the rule of thumb. They're saying that, okay, how much is enough for proportion? They're saying that if you have n times p and n times q, if they're both greater than 10, then they're saying that you have enough sample, okay, for your sample distribution to be what we call the normal. Okay, number three, the population size has to be at least 10 times as large. Why is it at least 10 times as large? Because in order to be a true simple random sample, each individual has to have an equal probability, right? We're never ever gonna have a true simple random sample. So suppose that we have 10 students here, and if we randomize and choose 4 students, we have 1 here, 1 student, and then all the way to 10 students here. 1 all the way through 10. Oops, 10. So far, so good? What's the probability of choosing a first student? Here, I'm going to choose 4 students. What's the probability of choosing a first student? Probability of choosing first student. Timothy? 1 out of 10. Very good. 1 out of 10. And then after choosing that, what's the probability of choosing a second student? Second student.
1 out of 10.
No, I already chosen one of them already.
Oh,
So 1 out of 9?
1 out of 9. Very good, right? What about probability of choosing a third student?
1 out of 8.
1 out of 8. Very good. You notice that simple random sample tells us before that in order to be a simple random sample, each individual have to have equal probability. Does it have equal probability? No, this does not. This has 1 out of 10. This is 1 out of 9, 1 out of 8, right? But you notice this right here. If your sample size is at least 10 times as that, so suppose if it's rather than dealing with say 100, so let's actually increase that 100, right? And then if you do 10 times is that, then that's 1 out of 10,000, right? So choosing a first person is going to be 1 out of 1,000. That's probably 0.00. Okay, that, right? And then what's the probability of choosing a next person? 1 out of 999. That's very close to 0.001. Okay, almost equal probable. That's why it is so important that you have what we call a large sample size, right? Okay, you have to have a large population, okay, which is states right here. You gotta have the population at least 10 times as large, okay, 10 times as large. Okay, and then if we do meet all those conditions, then your sample proportion, right, will be normally distributed with the mean of P and then standard deviation. This is what we call the standard error. Okay, it's a new standard deviation. We're just calculating it, right? And we call that same thing. It's a new standard deviation, okay? And you could calculate that by Q, okay? What is P and Q? P is probability of success, and then Q is probability of failure. Probability of, where Q is basically 1 minus P. Okay, it's always a complement of your probability of success. So for example, if I say, if I have P is equal to 0.4, okay, 40% is your success. What will be the probability of Q? What's the complement of that? That should always add up to 100%. What will be Q? 60%. So if this was 40%, then this has to be 60%. Altogether, it comes out to be what? 100%. Get the idea, right? So if I had P to be 0.3, okay, Michael, what is Q? Michael?
0.7.
0.7, very good. Okay, easy enough, right? Get the idea, right? It's always the complement, okay? So how do you figure out your standard error, right? This is adjusted standard deviation, basically, okay? You're adjusting to your sample, right? Yes, your standard error. And how do you get that? Using this definition right here. So we're gonna use a lot of technology. One thing is that they're not going to actually calculate your adjusted, right, standard error, which is our new standard deviation. Okay, so far so good. We do need to actually calculate this. Okay. Okay, we need to calculate that. Okay, for proportion. Okay, for central limit theorem for your sample mean, let's look at central limit theorem for sample mean. Okay, the requirement, the 3 requirement, right, for this theorem is that, again, your number 1 is always the same. It's very, very important, right? It's got to be simple random sample and independent, right? So number 1, it's got to be a simple sample and independent, okay? And for number 2, it tells us that you have to have a large enough sample size. What is large enough? You tell me. They're saying that, oh, if you have a size that is bigger than 25, right? Then we know that the sample distribution is going to be normally distributed. Okay, so far so good. Of course, your third condition is that your population size got to be large, at least 10 times as large. So these are the criteria, 3 conditions it has to meet in order for us to actually go about using what we call the technology to solve using a normal distribution. Okay, and this will be used right here, what we call the T distribution for this one right here. Okay, T distribution. Okay, and we'll use Z distribution. T and Z. Okay. And this is approximately normal. T is an approximate normal distribution, where Z is a normal distribution. Okay. So far, so good. Okay. One other thing is that your, again, standard error for your sample mean is going to be, right, or standard deviation is going to be your population standard deviation divided by square root of n. Okay. Any questions so far? So far, so good. Let's go through. So great. So we have these theorems. So how can we use them? Central limit theorem gives us the sampling distribution without having to do all the work for them, right? So they are best used when we're trying to answer a question about the probability of event involving the proportion and the mean. Okay, proportion and the mean. Okay, so draw the population distribution. Of course, all the population distribution, right? Draw the population distribution, labeling the horizontal, right? Shade the area corresponding to the probability of described event. Calculate the shaded area using the formula or technology. And most of the time, we're going to use the formula to calculate your standard error. And then we're going to use technology to calculate your probability. Okay, those are, so this is the first thing, calculate standard error. And then once we calculate the standard error, we're going to calculate the right probability, okay, using technology. So far, so good. Okay, any question? Okay, so when we see probability question involving group sample that is asking about sample proportion or sample mean, okay, our first step change, but the rest are the same. So use a population information and central limit theorem to draw sampling distribution if possible, right? Shade the area corresponding to the probability of described event. Calculate the shaded area using the formula and technology. It's the same idea, okay? One thing I want to point out is that the sample size n shows up in the denominator in the standard deviation in both variation of both versions, okay? Notice that as you increase the sample size, you will divide by a larger number, making the result smaller and smaller. This is an interesting feature, as it means the distribution is less and less spread out as we increase the sample size, okay? All right, central limit theorem. So let's ask, okay, central limit theorem answer statistic question. Okay, how do we know when to use central limit theorem? Okay, so how do we know? So when it's a key word here is basically, how do we actually go about using central limit theorem? So when you see a sample proportion or sample mean, then we're going to use a central limit theorem. That's it. Okay. Rather than a population mean and population proportion, then we're not going to be using central limit theorem. Okay. So if we look at one individual, use the population distribution. Okay. If we're looking at a group and taking an average or percentage, then use a central limit theorem, basic idea, okay? Which version of central limit theorem do I use? If it's proportion, use proportion. If it's mean, then use mean, okay? All right, so let's look at an example here, okay? Let's look at an example. According to the Oregon Bar Association, approximately 65% of the people who take the bar exam to practice law in Oregon passes the exam. Okay, only 65%. Find the probability that 67% of 200 randomly sampled people taking the Oregon bar exam will pass. So we want to figure out. Okay, so here, so they give us all the information. Okay, And if I ask you, what are they talking about here? Are they talking about a proportion or mean? Timothy, can I ask you?
Proportion.
Proportion. So therefore, this represents what we call, so according to the Oregon Bar Association, approximately 65% of the people who's taking the bar exam, right, to practice the law passes, right? So we know that P, in this case, let's actually gather our information. P is equal to 0.65. Now, Michael, can I ask what Q is then?
35.35.
Good. 0.35. Very good. It's just a complement. Anyone lost here? Okay. They add up to 1. Okay, or what we call 100%. So far, so good. Okay. And here, can I ask you, Alexandria, what is N?
200.
200. So I'm going to actually write this down. So N equals to 200, P equals to 0.65, Q equals to 0.35. So far, so good, right? And what we want to do is we want to figure out what is the probability of, say, P hat is, what's the probability that find the probability that 67% of the random sample taking the Oregon bar exam will pass. Okay, 67%. So it's going to be, what is the probability of 0.67? Okay, so far so good. And let's actually go back up here. Okay, so we'll go back up here. So far so good. Okay, and that's what we're trying to do. Okay, the definition of your normal distribution for proportion, you don't necessarily need to actually know this definition, but I'm going to show you the definition. The definition is Z is equals to P hat minus P over square root of PQ over N. Okay, so far so good. Okay, what we want to do is we want to normalize. Okay, and what we're trying to do is we're trying to figure out. So basic idea is that if this is what, if our, what we called our mean is 0.65, we want to figure out what percentage of people, 0.67, so percentage of people that passes. Oh, passes, I'm sorry. That is, okay. They're saying that what, 65% of the people actually passes, right? Let's see where we get here. Approximately 65% of the people who take the bar exam to practice law in Oregon passes the exam. Oh, so therefore, actually, 65%, yeah, so passes. So in order for you to pass, then it's going to be the area to the right. Okay, I think that's what we're looking at. Good. Okay, that's what we're looking at there. Okay, so first, so good. So now what we need to do, first thing that we need to do is we want to actually figure out, okay, going back up here, the two information that we need is your p-value, okay, which we already have, and your SE, standard error, which is your standard deviation, okay, which entails actually standard error, which is equal to square root of PQ over N. Let's actually solve that. right, with our calculator first. Okay, so we get P 0.65 times 0.35 all over 200. And let's calculate that. Sure. Let me give you guys a minute to actually take out your calculator. And also, in the meantime, right, I want you to also take out or open up your Stack Crunch, because we're going to be using Stack Crunch to calculate this. Okay. So the basic idea, the computation that you're actually doing is that we're actually normalizing this. Okay. What's the probability of P hat? In order to actually normalize this, let's actually erase this portion. That is actually greater than equal to, and I want to erase that. That should be greater than equal to. Okay, so in order to normalize this right here, we're going to take minus P. So we have 0.67 minus P, which is 0.65, divided by square root of PQ over N. And do we calculated this right here? What is PQ over N? Okay, for MVP point, who wants to actually answer this one right here? What do you get? If you put it in your calculator, what should you get for that? Anyone?
Does it need to be square rooted?
Yes. What did you get for MVP point?
0.03.
0.03. Very good. I get 0.03337268444. Okay, to be more precise. Okay, and who was that?
Alex Martin.
Then.
Yeah.
Okay, Alex Martin gets the MVP point. So therefore, we're gonna actually put that in the denominator, right? 0.033726844. Okay, and then this basically represents what we call the z-value, and we want to figure out the probability of that, right? So we get divided by the answer, we get 0.59. Okay, so far so good. Okay, and then we can actually calculate the probability, right? And that's probability. But so this is basically the background that you're doing, but you're gonna do this using technology. The only thing that I want you to actually look at is this one right here. I want you to say, oh, this is what we need to actually calculate. That's the only thing that you need to calculate. So let me actually switch off here, and then I'm going to go to the Stack Crunch. Okay. You guys should have all your Stack Crunches open. Okay, and what you want to do is go to Stack, calculate. Start, calculate. You guys are there? Okay, I'm going to be waiting a little bit. Okay, are we good so far? Let me get a thumbs up. Thumbs up, good. Thumbs up, good. All right, good. Timothy, are we good? Okay, good. So go to, in this case, we're gonna go to here. Okay, proportion. Okay, so stack, don't go to calculate, go to proportion stack. okay, because we're dealing with proportions. One sample, we only have one sample, and with summary. Click on that. Okay, the number of success, in this case, number of success is calculated for you. And where did you get that calculation? Okay, that was 137. So I'll show you later on where she got the calculation there. But it should be 100, oh, I'm sorry, 134. Let's actually put 134 there. Okay. Number of observation is the n value. Oh no, this is not right. Okay, this is not right. Calculate. Oh, we're calculating normal. Let's do, wait, proportion with data. Is that right? Confidence interval, no. Hypothesis testing. I'm not doing hypothesis testing. Let's see. Z1 calculate. Oh, it's got to be this. Even though this is proportion, it's going to be a normal. Let's see here. It's got to be normal. And we want something that is greater than. So we have mean to be, what was our mean? 0.65 with the standard deviation. Oh, we don't even have to do any of that. Oh no, standard deviation, we do have to calculate 0.0337. Okay, and that's all we need. And we want that to be greater than 0.67. And then we want to compute that. And that's what we're trying to get. Okay, what is the proportion greater than that? Okay. Anybody lost there? Everyone got that? Normal distribution. Okay, so it's the basic idea here is that, let me actually click this off and then share my, oh, stop sharing here. Okay, hopefully you guys copy that down or you have it in your, right? Screen here, start. Okay, so basic idea is that you just calculated this probability right here. This probability came out to be 0.27, approximately 6-ish, okay, or 27.6%. Okay, and that's what we get. Okay, but one other thing is that we should have already actually checked. Okay, checking to see that if you're what, so you does it meet the central limit theorem. Central limit theorem tells us that n times p has to be greater than or equal to 10, and n times q has to be greater than or equal to 10. So look for the conditions that we meet here. Okay, as you can see, n times p, n here is 200 times p, which is 0.65. That's going to be greater than, right? That's equals to 130. That's greater than or equal to 10. N times 200 times 0.35 is equal to 70. That's greater than or equal to 10. Okay, as we could see there. Okay, and then again, all we need is your two things, proportion, okay, and your standard error, which is what we call the standard deviation. And that needs to be calculated. So therefore, the probability, just like we saw here, your normal distribution here, and that is the probability right there. And what is that probability? How do you calculate that? And we did that with the normal distribution, okay? Even though it says X here, that represents just the proportion. We're just putting that X value. And if you compute that, we should get 0. I believe everyone got 0.2764. Yes, confirmation. Okay, good, thank you. Okay, confirmation. So the probability of 67% or more of 200 randomly selected organ bar exam, right, taker passes the exam is 27.64%. So far, so good? Any confirmation? Okay, all right, let's go through. Okay, let's see if we have, right, let's go through the last example here, okay? So let's look at membership in Mensa requires an IQ score that is above 131.5, okay? Which is, what do you mean Mensa? Have you guys heard of Mensa Club? I'm surely not in it. Anyone took a IQ test before? Anyone? Has anyone taken an IQ test before? I did. Well, I didn't officially take it. I took it online. Alexandria Lopez, did you take an IQ test before? You did? You mind sharing?
My score, but I took it.
Oh, do you mind sharing? No?
I don't remember my score. I know I took it, but I don't remember my score.
Oh, I don't think I took an official. I took online version of it, and mine came out to be 138. I think that's impossible because to be 138, you got to be like near genius level, and I'm not a genius of any mean. So I'm like going backwards, I think, right? So I think that's totally wrong. It's just the online version. I think it's wrong, big time, right? So they say to be a Mensa club, you have to have an IQ, right, above 131.5. Okay, 9 candidates takes IQ test, and their summary results indicate that your IQ is 133, right? The mean is 133, right? Score are normally distributed with the mean of 100 and the standard deviation. So these are the two information that we're going to be looking at, right? If one person is randomly selected from a general population, find the probability of getting someone getting an IQ that is what, more than 133. Someone getting an IQ of more than 133. But let's look at the conditions here. What is the conditions for this right here? Okay, so central limit theorem of sample mean, the require, right, is what? You can use the theorem if the sample is a simple random sample. And what is this right here? What's one other, your second condition, if we're talking about a mean? Your sample size has to be what?
25 or more.
Right, it's got to be large enough, 25 or more. Is our sample size large enough for our IQ test here? How many samples do we taking? If one person, right?
9.
9. Or did they indicate 9? They're saying that, oh, 9 people here, 9 candidate takes the IQ test, and their summary result indicates their IQ score of 133. So is this sufficient for our central limit theorem?
No.
No, it's not sufficient, right? Okay. So notice over here, notice this question is only asking about an individual. We don't need a central limit theorem here, okay? So even though we don't have enough, right? They're only talking about an individual, not as a group, right? If it's for a group, then you have to actually, right? So indicating that, right? And one other thing is that if your population distribution, okay, I don't think they mentioned here, if you know the population distribution is normal, if your population distribution is normal, it doesn't matter how big of a size you take as a group, right? Doesn't matter if it's size 4, size 6, size 16, right? As a group, it's still gonna come out to be a normal, okay? If your population distribution is normal, okay? So it does not have to meet, if your population distribution is normal, then it does not need to meet the CLT, okay? Central limit theorem, okay? And we already know that the IQ test is actually a normally distributed, okay? Okay, your population is normally distributed. And that's for that reason as well, we don't necessarily need the central limit theorem, okay? It doesn't have to meet the criteria for central limit theorem. So now, once we know that the mean is what? That's our population mean, and what? Population standard deviation, right? What we want to do is we want to figure out, right, the sample mean. What is the sample mean? X bar?
100?
Nope. Sample mean. So it says the 9 candidate takes the IQ test and their summary result indicate their mean of 133. Your sample mean is 133. Okay, so far so good. Okay, and what? Your new standard error is gonna be 15, okay, divided by square root of 9. Okay, and which it calculates to be, that's your standard deviation, new standard deviation. 15 divided by 3 gives me 5. So that's gonna be the two information that we'll need. Okay, so we have the, oh, right. So these are the information here, results, and this is what we need here. Okay, so this is what they get for the first one, right? Calculate if one person, so if you use technology to actually calculate that, if one person is randomly chosen, the probability IQ is above this is going to be only about 0.0139. But when you actually realize that you're, right, okay, it's a random and independent sample if you're large and popular population, using the central limit theorem, then your calculation for this to be larger than this is going to be very, very small. Okay, so work on this one and go through with Michael and Alex, right? And then they'll help you actually use technology and show you how they got these values here. Okay, so far so good? Okay, all right, so I'm gonna give you guys, I'm gonna leave it here. Okay, and then I'll see you guys, I guess, on Monday, right? Okay, all right, okay, all right. All right, good luck with your second part of your homework too. Second part of your exam, okay? All right, I'll see you, and then let me actually, Alexandria, make a co-host there, and then I'll make Michael a host, and then I'm gonna leave. All right, goodbye. See you guys later.
All right, guys, let's go on a 5-minute break. 11:28, we should be back.
Did he say he'll see them Monday? You're muted.
I don't know. I didn't hear.
Yeah, I was like, I kind of caught that last part.
Oh
But
no.
he does know today's Thursday, right? And we have class tomorrow.
I don't know.
Okay.
All right, guys, so we were here. We just want to check this on StatCrunch, right? Okay, so let's see if I go into StatCrunch. So in this example, we were trying to figure out what the probability is that somebody has an IQ bigger than 133, right? With a mean of 100 and standard deviation of 15. So if I go to StatCrunch here, and I go to Stat, Calculator, and then Normal, Stat, Calculator, Normal. It lets me choose it. Stat, Calculator, Normal. Our mean was 115 standard deviation. And we want to know that when it's going to be greater than or equal to 133. So we need to change this sign to give us greater than or equal to. I don't know why mine's not letting me. 133. And then you would press compute. Now, make sure you change this to greater than. Oh, there you go. Perfect. And so we get the result is 0.0139, which is exactly what the textbook has, right? So for most of this, you're going to be always using the same thing. You're going to go Stat, Calculator, Normal. And then from there, you're only going to put your mean, standard deviation, and whatever you're trying to cancel. You're trying to calculate, whether that's greater than or less than, or sometimes in between two values, right? And then let me just check that there wasn't anything after this. Oh, is this the one we were trying to do instead? Okay, let's do this one. That one was 100 and standard deviation 5. So Stat, Calculator, Normal. $100, 5, greater than or equal to 133. And then press compute. And we get this number, 2.0 something e to the negative 11. Now that e to the negative 11, that's just telling you that you're moving the decimal place 11 times to the left. So this number that you see here, that's the actual value, which is pretty much a 0, right? It rounds to 0. Okay, and so that was the textbook there. Now we're gonna go ahead and start on the homework. So this guy here. Okay, and in module 11, we're going to be looking at 2 types of sample distributions. Let me bring out my little cheat sheet that I have, like a little notes. All right, so these are my notes right here. We either have sample proportions for p hat, or we have sample means for x bar. The requirements are in white. We have 3 requirements using the central limit theorem for both of them. And the results are in pink. Right, the first number we have, like for example, on the first one, is p 2 dots and then n parentheses. The first number is always going to be your mean. The second number is going to be always your standard deviation. Same thing in the sample means. And underneath, I just put some letters that you should know the meaning of, but I just put them in case we forget. Okay. So now, the first step with these word problems is figuring out if we're gonna have a sample proportion or a sample mean. So anytime that you guys see means, mean is taking the average of something, right? So anytime that you see average is gonna be most likely a means. If you don't see average or means, it's most likely gonna be a proportion, all right? So let's go ahead and identify what each of them are in sample, in mean or proportion. So let's say number 1, can you read it, Destiny?
The last time such statistics were available on the M&M's website, the stated proportion of the blue M&Ms were 24%. Since Joel's favorite M&M color is blue, he usually hopes to get more than usual. If he takes a simple random sample of 55 M&Ms, what is the probability that he will get more than 30% blue M&Ms?
Okay, perfect. Now, Destiny, do you think this is a means problem or do you think this is a proportions problem?
Proportion.
Proportions, right? Because we don't see the word average or means anywhere, right? So this is gonna be a proportion problem. Proportion. Okay. Now, we need to calculate a couple of things. We need our P, we need our Q, and we need our N. And then for the central limit theorem, we need to satisfy 3 requirements, 1, 2, and our third one. So our P, our proportion here, proportion is gonna be talking about the population, right? So I'm gonna go ahead and box in all the numbers that I see. So I see this 24%, I see this 55, and I see this 30%. Okay, now, out of those ones, which one would you say is N? N is the sample size.
$55.
Perfect, 55, because that's the only one that doesn't have a percentage, right? That's talking about how many we have, okay? Now, which one do you think it's P? Do you think it's 24% or 30%? P, by the way, is the population proportion.
24.
24%, yes. And so they tell us here, we have the proportion is this. This number that they give us down here, more than 30%, that's just relating to a question they're asking us right here. If what is the probability that it'll be more than 30%, right? So that's gonna be in our, what we're trying to solve later on. Okay. Now, to the requirements for the central limit theorem is number 1, that is a simple random sample. Now, to be able to tell that, the problem most of the time has something that tells you that it's random. So if you just look at the problem, you want to look for something that says random. Here we go, simple random sample, right? So since they mention it, then we have a simple random sample. So that one's satisfied. The next one is that N times P is greater than or equal to 10 and N times Q is greater than or equal to 10. So N times P greater than or equal to 10 and N times Q is greater than or equal to 10 as well. So N in our case is 55 right there. And P is 0.24, greater than or equal to 10. So if we go ahead and multiply 55 times 0.24, we get 13.2, which is greater than or equal to 10. This one it is, right? Okay, but we also have to check that the other one satisfies as well. And so now Q, we can calculate Q. Q is always 1 minus P. So it'll be the complement of P, which is 0.76. So 55 times 0.76. That's equal to 41.8, which is greater than or equal to 10. So then the second requirement is satisfied. Okay, and then we have our third requirement, which is n, capital N, which is the population size, is greater than or equal to 10 times little n. N is the sample size. We want n greater than or equal to 10n. So n is 55, so 10 times 55, that's equal to 550. And so is n, capital N, greater than or equal to 550? Now, this one is not, they don't tell you in the problem. You kind of have to think about it a little bit. So what's our population size here? We're looking at M&Ms, right? Okay, so we're talking about M&Ms in a packet. Do you guys think there's more than 550 M&M packets in the world? Yes, right, obviously. So then because we know that, then this one is also satisfied. So we already satisfied all three requirements. Now we can move on to the results. So up on the left here, we already got the requirements, results. I get p hat and then 2 dots n parentheses p and then this other guy. So I'm gonna write it right here. Square root of p, 1 minus p over n. All right, so that's our result there. This first number, that's our mean. And then this is our standard deviation. Now this n here, even though it's capital N, and we're used to capital N being the population size, when we have a capital N in front of 2 parentheses like that, we're describing that we have a normal curve. Okay. So now let's find out what these two numbers are. So P, up on top I have is 0.24. And then if I calculate square root of P, which is 0.24 times 1 minus 0.24 all over N, which is 55, plug that in my calculator. And I get 0.0576. Let's keep it at 3 decimal places, so let's just make it 8 right here. Okay, so this is our mean. This is our standard deviation. Okay, so we calculated what we need. Now we can answer the question. So they want to know if he takes a simple random sample of 55 M&Ms, what is the probability that he will get more than 30% blue? So 30% and more than. Okay, so we're looking for the probability that are in StatCrunch, we're gonna be using the X, and it's gonna be greater than or equal to 30%, so 0.30. So this is what we would wanna look for in StatCrunch. And for the mean and the standard deviation, we're gonna use this number here. So this is what we're doing now. Okay, so I go StatCrunch, and I want the standard. My mean was 0.24. My standard deviation 0.058. And then greater than or equal to, that's exactly what I wanted, and I want greater than 0.30. 0.30. Okay, and I calculate and I get this number there. So that's 0.1505. So this is equal to 0.1505505. If we turn this into a percentage, this is 15.05%. And that would be your answer right there. Okay. When you're doing this, you also want to, in your work, include a sketch of what StatCrunch gave you. So your mean was 0.24, and 30% would be somewhere right here maybe, and then shade to the right, right? So your homework should have that little drawing too. Here, I'll go back to it.
Do we have to turn in this homework?
Huh? Yeah, you're gonna be turning this in. The due date, I'm not 100% sure.
Oh.
Any questions on this one? Okay. Okay, now we're gonna go to number 2. Can you read it, Timothy, please? Number 2.
Alex is hoping to make some money using a popular trading card game. Does that say heart or hearth?
Hearth. I don't know what it is.
By buying and selling cards to players. When buying randomized packs, the cards worth the least are the most common, and the cards less frequent as their value goes up. Assume the average price of an individual card is 20 cents with a standard deviation of $1. If Alex buys a pack of 15 cards for $4, what is the probability that the average value of cards will be greater than 27 cents per card, just enough to make profit by selling all 15 cards?
Perfect, thank you. So do you guys think this is gonna be a means problem or a proportion problem? If it's a means, it should say means or average somewhere.
Mean?
Mean, perfect. And that is because we see, where was it? I just saw it. Oh, average price, right? So because we have average, we know this is gonna be a means problem. Okay. So for the means problem, we're gonna need to know what, sometimes they'll tell us what the population average is. The population mean. It'll also give us maybe the standard deviation of the population, and N, our sample size. So now we're looking at the one on the right. Okay, so we need to satisfy the 3 requirements for the central limit theorem, which one is gonna be if it's a simple random sample. For that, we need to look at the problem and figure out if they let us know that this is random. So if we look at this, you guys see this little word right here, randomize. I boxed it up. So then that's telling us we have a simple random sample. Okay. Then the second requirement is that N is greater than or equal to 25 or the population is random. Now, if we were to calculate N is greater than or equal to 25, let's figure out what our numbers up here are. So I'm gonna go ahead and box the numbers that we have. We have 15 there, this guy there, we have $1 here and 0.20. All right, so we have $0.20, we have $1, we have $0.27, 15, and this number, I guess, $4. So what is the N? What is the sample size out of those numbers?
Is it 15?
Yeah, perfect. Because all the other ones are percentages, right? I mean, are values of money. So 15 is the only one that's not a value of money. That's telling us how many we have. We have 15. Now, the other two, we have, the first one is gonna be our population mean. Put it on individual card. And so that's gonna be given us by this. The individual card is 0.20 with a standard deviation of 1. Most of the time, these two will come together. So this guy is a standard deviation. So they told us standard deviation is 1, and then the mean up here is 0.20. Okay, so now we can calculate this. N is 15, so 15 greater than or equal to 25. 15 is not greater than or equal to 25, right? So this is not right here. But if you look at our second requirement, it gives us another option. It says, or the population is random, right? Now here, we have it randomized, and they also told us the mean and the standard deviation. So here we have a normal distribution. So this is gonna be a random population, okay? And so then it would satisfy the second requirement there. And then lastly, our third requirement, we want that capital N, which is the population size, is greater than or equal to 10 times little n, which is the sample size. So n greater than or equal to 10n. Little n is 15. So then this is n is greater than or equal to 150. Now, what are we talking about here? We're talking about some cards that they're using, right? Do you guys think there exists more than 150 of those cards? Probably, right? If they have a whole game going, so then we would say this also satisfies. And so now we satisfied all three requirements for the central limit theorem. Now we can use, so we're gonna have, the result is X bar. Okay, so our result, normal distribution, our mean, our standard deviation, perfect. So these are gonna be our results. Now if we plug in the information, we would get mu is 0.20 from the top. Now, standard deviation is here 1 divided by square root of n, which is 15. So if I plug that in my calculator, 1 divided by square root of 15, I get 0.258. So this is my mean, and this is my standard deviation. Okay. All right. Then after that, let me read what they want me to find out, what they're asking for. It says, the last sentence, if Alex buys a pack of 15 cards for $4, what is the probability that the average value of the cards will be greater than 0.27 per card? So we want to find out the probability that we have our X, they're gonna call it in StatCrunch, greater than, so we're gonna have greater than or equal to 0.27. That's what we wanna find out using this as our mean and this as our standard deviation. So go to StatCrunch again. We have it here. Let's see, mean is 0.20. 0.20. Our standard deviation is 0.258. 0.258. Okay, and then we want to figure out when X is greater than or equal to 0.27. Okay, and then we press compute. And we get our answer right there. It's 0.3931. 3931. And then make sure you also include your little drawing. Yours are gonna look better than mine, of course. My mean was 0.20 and 0.39 is somewhere above. So you would shade on the above part. If we change this to a percentage, it'll be 39.31%. Anybody have any questions so far? We're good? Okay.
Is there going to be a tutoring after this, going over the homework?
Yes, I'm gonna be there.
Okay.
And I think there should be more hours later on as well.
Okay.
All right, now let's go to number 3. Michael, can you read number 3?
Yeah. And investigating how much time his classmates on social media per day, Ruben found that for the whole class, 118 people other than themselves, the times were distributed normally. The mean number of hours was 2.3 and the standard deviation was 0.9 hours. If Ruben were to choose 4 people at random to form a study group with, what is the probability that they would spend less than average 1.5 hours on social media per day?
Oh, perfect. All right. So now, do you guys think this is a means or a proportions problem? If it's a means problem, it should have the word average somewhere in the problem or means in the problem. If it doesn't, it's probably going to be a proportions. So it says mean, right? The mean number of hours. So then this is going to be another means problem, just like the one we did right now. Okay. So for all my mean problems, I'm going to probably find my this is my mu, my population mean, my population standard deviation, and my n. And then I'm gonna have my CLT requirements, number 1 and number 2. Okay, so here, let's see. The numbers that I see are 118 people there. I also see a 2.3 right there, a 0.9, 4 people, and an average of 1.5 hours. That's all the numbers that I see. Out of those 5 numbers, I need to figure out what is my little n, my sample size, my alpha, which is my standard deviation, and my mu, which is my population mean. So the easiest one to figure out is n. What's my sample size here?
4?
Yes, 4. So we have the options of this one or this one there, right? Now this is the whole class, so this would be actually the this is the population and this is the sample. Okay, now what is the mu? What is the mean? And most of the time these two come together. Right, so the mean hours was 2.3. And the standard deviation was 0.9. Okay. Now, okay, central limit theorem. So the first one is if it's a simple random sample, which is it? We need to look at the problem and figure out if they said simple random sample anywhere. Random. You see that word, random? They were choosing at random. So we have a simple random sample. Okay. The second requirement is, I don't know what happened to my thingy, but the second requirement, it was that n, little n, was greater than or equal to 25, or that the population was random. Population random. So for this, little n is 4, which is greater than or equal to 25. That is not true, but we have a random population here. So this one does get satisfied because of that. We have a random here. We also have that the times are normally distributed. Normally distributed will let us know that we have a random population. And then the third requirement was that n, capital N, was greater than or equal to 10 times little n. Little n is 4, so this is capital N is greater than 40. And n, what are we talking about here? We're talking about people, right? People in the class. Now we have a total of 118 people. So it's 118 greater than or equal to that 40? It is, right? So then we already satisfied all 3 requirements for the central limit theorem. I'm gonna leave the rest up to you because we're over the time. Any last minute questions? All right. Bye guys, have a good one. I'll be in open tutoring right now.